Welcome everybody to the third video in a set of videos where we discuss the topic of tuning the data warehouse. My name is Joachim Snygg, and this video is a part of the course IS5 Data Warehousing that is given at Stockholm University. In this video we will discuss designing aggregations and then especially, of course, designing data warehouse aggregations. So, a major point in dealing with data analysis is that the foundation layers of all dimensional data warehouses have a huge number of records, right? And this large number of detailed records is needed not because an analyst is going to need a single record at this level. We usually are not that interested in finding out who bought that package of pink tissues, for instance. We usually look at summarized data on a higher level. But we still needs this single records because the analyst must be able to make very precise cuts between the records. So, for instance, if we look at pink tissues, we might not be that interested that Ove Johansson bought a package of pink tissues, but we might be interested in seeing that pink tissues is our number one sales item, for instance, in a firm. Okay, so if we don't track the individual accounts, we cannot group accounts into the most interesting clumps. So that's why we need detailed data. And if we don't track the lowest level product subdivision, then we cannot pull out all the groups of products we might want to track. So we need the base level data, but we usually look at it in a summarized manner. So even though many queries will opportunistically need to retrieve clumps of base level data, most queries will relax the constraints of the dimensions. And if all we have is base level data, then relaxing constraints on one or more dimension means that we let a vast number of records into our query. And as you all know, this will affect the performance of the search. If we need to search through 1 million rows, then that will take a longer time than if we need to search through 100 rows. It's as simple as that, basically, the basic idea. However, the problem is that we still need this base level data with a lot of rows. So consider the queries. How much total business did my newly remodeled stores do compared with the chain average? This question, I believe it might be a relevant question for a manager to ask, a business analyst to see when you do your analysis. So this might be a very relevant question. But when we look at it, and then especially if we consider the granularity, the level of detail of products and stores, what do we see? Well, for this question, we see that we need specific stores, but we are summarizing overall products. Okay, consider this query. How did leather good items costing less than $5 do with my most frequent shoppers? Think a minute about this. The idea here is think about products and stores. What level of detail are they on? Well, we need specific products, but we're summarizing across all stores, right? So this is the opposite of the previous query. We see here we need the opposite level of detail. So we need specific stores in the first case, and in this question we say, well, we summarize across all stores, and then the same with products. We tip it over, flip it over. A third query. Think about this, what it does to our store and product level of detail. What was the ratio of non-holiday weekend days total revenue to holiday weekend days? What does that mean for the grain statements of stores and products? Well, we need specific days on the calendar, but we're summarizing across both product and store. Excuse me. In all three cases above, we need very detailed data from one of the major dimensions, but we are either summarizing or omitting detail from some of the other dimensions. So all of these questions will be expensive to process if we only have base level data. And this is a conundrum, the problem that we have to deal with. So what is needed here is a set of several different pre-computed aggregates that will accelerate each of these queries. But we still need to keep the base level data, so we'll add more star join schemas, if you like. We need to add more dimensions and fact tables to capture this, or other types of aggregates. So it is typical to expect anywhere from a 10-fold to 1,000-fold improvement in runtime by having the right aggregates available. So aggregations can be created on the fly or by the process of pre-aggregation. And then, of course, pre-aggregation is the most efficient because you have to do less during the query. You do less if you have pre-aggregated something. Well, then you don't need to pre-aggregate it when a business analyst makes a query. While if you do a question on the fly, then the business analyst have to wait for the on-the-fly aggregation. So in its simplest form, you could actually say that an aggregation is a SQL SQL group by statement, which would be on the fly. Then you can create a view and so forth. And then the highest form would be materialized views, pre-aggregations of materialized views. So the use of pre-stored summaries, aggregates, is the single most effective tool the data warehouse designer has to control performance. An aggregate is a fact table record representing a summarization of base level fact table record. An aggregate fact table record is always associated with one or more aggregate dimension records. So, for example, in a base level fact table dimensioned by UPCs, which stands for Unified Product Code, so it's an individual product, right? In a base level fact table mentioned by UPC level products, individual stores and individual days, then we can imagine the following aggregate records. Category level product, there we have aggregates by store by day. District level store, where we have aggregates by product by day. Monthly sales aggregates by product by store. And then we will have category level product, which aggregates by store, district by day. So, and final category level product aggregates by store, district, and by month. It's also important to note that of course these subsets of attributes are conformed dimensions according to the Kimball approach. We will say that we will use conform dimensions, strict mathematical subsets of the base level dimension table. So, how to store aggregates? Well, we have two choices. As new level fields in an already existing model, or as new dimensions and fact tables. That is, we create a new dimensional model, we create a new star join schema, for instance. So, how does new level fields work? Well, so in this example, the date dimension, store dimension, and promotion dimension, they are exactly the same as in this previous, and therefore I have a simplified notation where we just show the table names. This means that, okay, we have an exact set. It's the exact same table basically. So we have a conform dimension, which is exactly the same. But in product here we have changed the attributes by adding a level attribute. So in the level attribute here we can store which level we are talking about when we are talking about a product. So here is an example of sales fact and product D. This is on baseline level. So we can see in 1st of May we have sold the product P12 for $100, and then we can see the product P12 is pink napkin, our favorite item in our stock. And we can also see that a pink napkin has a subcategory, it's napkins, and in the subcategory napkins we also have white napkins and red napkins. And those belongs to the category of paper. And in the category of paper we don't only talk about napkins, we also talk about tissues. And tissues, where there we have the eco tissue, the Lambie tissue, for instance. And in the fact table you can see, in the fact table you can see here the dates. So 1st of May, 2nd of May, 3rd of May, 4th of May, and so forth. And here you can see the individual products, and here you can see the facts, the amount sold. So if we want to ask, if we have the 3 queries, sold napkin per day, sold tissue per day, and sold paper per day, then we need to make summarizations when in the application tool. So if we have 1 million rows, then those summarization will take some time, and we want to fix everything as quickly as possible. People's attention span is very short, and I think you have like a few seconds. I've heard different numbers of seconds, but it's like 7 or 8 seconds before people starting to lose patience. So you need to be very efficient to create a tool and a query that is sufficient. So what you do here is you add this level field. So this is the original, from the original product we have base level. These are the napkins, and these are the eco and Leni tissues. And then this we can see up to here is the very same rows. Then we add in the fact table P10 and P20 for the 1st of May. Well, that means that, okay, we group on subcategory. So then we will see that, okay, if we look on 1st of May, we have sold, if we look at napkins, we will see the first row, P12, that is pink napkins, so that's 100 for napkins. P11 is also a napkin on 1st of May, so that's 300 napkins in total. And then P25, well, that's not napkins. So then we will say we have sold 300 napkins. But instead of doing that summarization, we can directly go to the level of napkins, P10. And then we look at 1st of May, P10, and then we see 300, and then we can directly access that row without having to make any calculations. And think of this as like million of rows we go through, then we just access it here, then it's just touching one row, so it will be very, very fast. we just have to scan through, and we have just to perform a table scan in the sales fact table until we meet. I guess we could probably even use an index, as we talked about in the last lecture. So this will be a very, very fast and efficient search. However, and then of course we can also look, well, if we look at the next level, we can look at a paper. So if we summarize by category, then we will see that 1st of May we have sold 300 tissues, and then we have actually sold 300 napkins, and then we have actually sold 300 tissues as well. So that means 600 together, and then we can go to P100 on the 1st of May, and then we can see that, okay, 600. So this is on another level. Yes, so here you can see the added rows in the fact table and the added rows in the product dimension. But nota bene, constrain the queries to avoid double counting of the level fields, because if we're not careful, then we can look, okay, how much have we sold on on the 1st of May? And then we can see, well, we have sold for $600, basically. But if we don't watch out, we will see, okay, 1st of May, 600, and then we have 300 there. So we have 900, 1200, and 600 there as well. So $1,800 it would show us if we don't add a constraint that says only look at base level. So it will be a more complex query, right? And you need to to have constraints when you perform a query, and that is perhaps not as efficient as it could be. So is this a solution you would choose? Seems really good, doesn't it? So just think, yay, and then we will look at why you're wrong. So what we can do is we can create new fact tables. Then we don't have to deal with constraints. So then we can be even more efficient when we create our queries. So we will have one dimension tables that deals with the base level of products. So this is just exactly the same as the original table, right? And then we create an aggregate on subcategory level, where we store sales fact for subcategory, but not for the base level. So this will only contain the rows P where we have P10 and P20 only when we have the subcategory levels. So it does not store base level data, and it does not store category level data, but only P10, P20, P10, 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 P20. And category product, that's another aggregate that we create. So now we will have 3 star join schemas instead of 1. But if we are going to create a search on subcategory level, well, then we go directly to this and we don't have to deal with anything else. And then we will be really efficient, and we will have a query without any constraints, just straightforward. Show me the money. Show me the money. Okay. So this is an example of how the new fact tables will actually look like. This is the product dimension. This is a subcategory product, and this is a category product. And then we will have a base sales fact table for the product dimension. We will have a subcategory aggregate sales fact table for the subcategory product. And here we only store. So now if we look at how much did we sell 1st of May, then we can see 300 on subcategory level. And here we have, I don't have all the rows here, and here we can see category aggregate sales when we just look at the category paper. So you can either choose new level fields or you can choose new fact tables, and new fact tables is very much more efficient when querying questions. But of course you need to think of the creation of an aggregate fact table requires the creation of a derivative dimension, and depending on the original then, and an artificial key for each new derivative dimension. And the artificial key here is, for instance, P20, P10, P100. That's new artificial keys to deal with this. These new aggregated dimensions are conform dimensions. And conform dimensions do not have to be exactly the same. In this case, it's a subset of another dimension, but it's a strict mathematical subset, right? And a conform dimension can be a vertical or horizontal subset. Yes, we don't really have to bother about that right now. So, how to store aggregates? As new level fields in an already existing fact table, well, we will have problems with double count. And this will also be visible for the user. So even if we know it, we have to educate the user to understand how this structure of that one sale, depending on the key, represents, and depending on which level it is, you can summarize it or not. So this is not good. We want to make it as simple as possible for our end users, because we don't require our end users to know anything about data storage or data warehousing techniques, or our end users should not need to look at this video in order to be able to maneuver in their business analyst work. Well, if we look at new fact tables, what are some benefits from that? We will see that we have no problems with double count. It's invisible to the users, are easily introduced and or reduced at different points in time, because if we add new dimensions or new dimensional models, that does mean that the old can still work. We just add more. We don't have to stop every analyst work to update the data warehouse. We just insert more solutions. And we will have simpler metadata, because we don't have that much to care about, while in the complex new level field, then we need to capture this by having metadata that helps us. It's a simpler choice of key, and the size of the field for the summarized data does not increase the size of the field for the basic data. However, sometimes it might not be advisable to create an aggregate, and that is when we are when we might risk having a sparsity failure. A sparsity failure deals with the planning of aggregate table sizes that can be tricky because of this phenomenon. This phenomenon appears when we build aggregates on very sparse tables. For example, in the grocery store item movement database, only about 10% of the product in the store are actually sold in a given store on a given day. And even disregarding the promotion dimension, the database is only occupied 10% in the primary keys of product, store, and time. However, when we build aggregates, the occupancy rate shoots up dramatically. If we sell just one single tissue product, we still need to create 2 more rows, an aggregated row for tissue and 1 for paper. So that's the general idea. Think of that we're having these three star join schemas, one for the base level, one for the subcategory, tissue or tissue, or what the other word was, I've forgotten now, and a third for the paper category. So here, if we only sell 1 packet of pink tissues on 1st of May, even if it's only 1 small package, we need to update it in 3 different dimensional models. So that means that we will, that means that with very diverse sales, where one product or one category has very few cells, for instance, then our data warehouse will grow increasingly quick, 3 times as quick as if we did not have the aggregate. So sparsity failure is something that you really should consider. You need to analyze your data to see if it's a good solution or not. Yes. So here is an example where we can see the percentage of sparsity in different ways. So assume we have 10,000 products within 2,000 different brands. We have 1,000 stores within 100 districts, and we have 100 weeks within 30 months, roughly. So then we will see that on the base level, product by store by week, we have 10,000 products, 1,000 stores, 100 dates, and that will have a sparsity of 10%, which will affect 10 million rows. One way, we have brand by store by week. We will then have 2,000 products, 1,000 stores, 100 days, and then we will have 50% of sparsity. So here you can see 100 million rows. And here you can see that, for instance, if we have a two-way brand by store by month, we would have 2,000 products, 1,000 stores, and 30 days. Then we would have a sparsity of 80%, which would create 48 million rows. So you will see here that the sparsity failure would really grow the amount of rows we need to deal with in the fact table, and then that would not help our efficiency. Right? So the last topic we're going to discuss in this video is that, of course, if you don't suffer from the sparsity failure and you have several different dimensional models, then it's hard for the customer, for instance, the end user, to keep track of which cube should I load, which dimensional model is the best here. So we don't show this to the end user, that we have all these different models. Instead, we let an automated aggregation navigator keep track of this. So we have the query tool client or the application server, and then they put in base level SQL statements. They translate the user query to base level SQL, and the aggregate navigator looks into the aggregation metadata and then writes aggregate aware SQL and say, okay, go to the subcategory fact table for this. And the database management system then does that and do the table scans on the subcategory fact table, for instance, and the aggregated results are given back to the aggregate navigator, and the aggregate navigator passes this on to the query tool client. So without the user knowing it, we have used our aggregated tables. So the navigator chooses where to search, if we should have the baseline table, the subcategory, or if we should have the category product, without us knowing. We just see the sales cube as end users. So this is just a simple example of how to rewrite the query. So if we say we have a sum here, and then we can see the aggregator will see that, okay, we have a sum, then we'll have a group by, and the group by is by category. And then it will access its metadata, and it will see that, okay, so instead of accessing base sales fact table, we access the category sales. We should access the category sales fact table. So we'll send this information to the DBMS. And instead of accessing the product dimension table, the aggregate navigator suggests that we should access or tells the DBMS to access the category product. So the aggregate navigator rewrites the query to using these new category sales fact and category product instead, and in this way the database management system just gets the SQL query they need, and the end user, they just see the SQL well, they don't even see the SQL query, but they will only see the thing that they asked for. So this is the aggregate navigator does this without the end users and even the database management systems knowledge. So a summary. Pre-aggregation demands more storage space but provides better query performance. Lowest level of aggregation is determined by the granularity of the fact table, and aggregation is easier when facts are all additive. So if we have semi-additive or non-additive facts, aggregation is more complex. Again, the beautiful pictures are from a 14th century songbook called Codex Manesse that is available in digital format from the University of Heidelberg. You can see the address below. So thank you for your attention.